I think we can start today's webinar. I will be admitting the participants as they are coming more and more. Hello, everyone. First of all, welcome to today's webinar. This is Emine once again, Head of Sales in VRLab Academy. Today we are here with Mehmet Salih Gencer. We had planned to have Beril Tekin join us and give a presentation on laboratories in the AP curriculum too, but due to some health problems that arose at the last moment, she could not join us. So we hope you will meet her in our next webinar. So now I'd like to start with an introduction, and then we will continue with the presentation followed by your questions. Mehmet Salih Gencer has completed his 15th year this year as a physics teacher and has had the chance to teach in 7 different schools in 7 different countries, and has so far taught IB, British, and American curricula. He is currently teaching physics in the IB curriculum at Emirates International School in the UAE and hopes not to change countries in the near future. So please feel free to write if you have any questions to the Q&A section during the presentation as well. And I'll be directing your questions to Mr. Gencer at the end of the presentation. So now I give the floor to him.
Hello, everybody. Welcome to the presentation. It might be good morning, good afternoon, or good evening. Here in the UAE, it is 9 p.m. And hopefully this is going to be a rich presentation for all of us. As an IB teacher, I am in favor of communicating the information in a student-centered manner. So this is going to be a bit of a challenge for me to be the one all the time, like a talking head. Hopefully you will be participating with your questions, and I will be more than happy to answer them at the end of the session. So the focus of our presentation will be on the new IB diploma program in connection to the IB sciences. In here it says curricula. However, the middle years program actually is not a curriculum, but a framework in which many different curriculum can be adapted into. But IB provides more sort of a curriculum, and it has some new adaptations or new direction in the following year. So there are 3 main topics that we will be talking about: what is new in the IB, conceptual learning, and finally we will be ending the presentation with concept-based inquiry. Before I start, I would like to get your experience in IB in teaching so that I can somehow adjust my content depending on your answers. I would be more than happy if you can just take the poll for a second. And just to keep in mind that this presentation for all of us, it is aimed for all audience groups. Therefore, whether you have teaching experience or not, whether you have IB experience or not, there will be always a part in which you can benefit from, I hope. We have got some options for the AP curriculum as well. However, Miss Beril is not able to join us today, unfortunately. So we have got more than half with no teaching experience. You've got 30% with IB experience, 2 people with IB experience, and 1 person with only other curriculum. Okay, thank you very much for your answers. So what is new? The IB diploma program is a 2 years program before the university. And now it has made some adaptations in the new curriculum. There's a shift away from the theory heavy content towards more hands-on learning. No more options. In the past, there were given options in which students choose and study and take an exam on whichever content they have chosen. Now, these content have been embedded into the main content. There are new roadmaps that allow for the interconnections of concepts, contexts, and content embedded in course structure. In our presentation today, we will be focusing on concepts. The idea of concepts are already in the middle years program, which is a 5 years program before the DP. Greater emphasis on conceptual learning, meaning that concepts are embedded into the course structure. And what I understand from concepts and how IB understands concepts can be quite different. So we will be looking into that. We will have another poll trying to predict the concepts that are focused in the middle years program after we study the concepts that are introduced in the new diploma program. There will be guiding questions to guide inquiry and connect content to concepts and themes. We will be going through a content in which we will be talking about the use of virtual reality laboratories and applications of VR. Linking questions support the creation of networked knowledge and cross-cutting connections. And this is a repetitive key term in the program, network knowledge and cross-cutting connections. We will be also looking at interdisciplinary units and application of these network knowledge and cross-cutting connections while we are talking about the content. A greater emphasis on skill development. So we are shifting away from the content-heavy curriculum into skills. In those skills, we are going to integrate inquiry. It's already there, but we are going to have more emphasis on exploring and designing, collecting and processing data, and concluding and evaluating. In the middle years program, these are already integrated as 2 of the 4 objective domains. The tools will include experimental techniques, technology, and mathematics. There will be no more prescribed practicals. In the past, there were a list of practicals that every DP student has to do. Now, the shift is towards prescribed skills. And those skills include thinking skills, critical thinking skills, experimental skills. So what is conceptual learning? We will go through the understanding of conceptual learning. We will talk about a bit of theory now, and then we will look into how we can apply this theory into an application. What is conceptual learning in IB? Concepts are mental representations of categories. They are constructed in the student's mind, modified and activated by the learner through learning experiences. Concepts do not exist in isolation, but are interrelated. Conceptual understanding is always a work in progress. It is continually being developed and refined. Conceptual understanding is therefore an outcome of a non-linear, ongoing process of evolving understanding, adapting previous understanding, and identifying and dispelling misconceptions. I would like to focus on the non-linear part. And while I talk about the example that we will be discussing about, we will have different connections. Generally, as a teacher, most of the time, we have our comfort zone. We start from in a unit, we start in an order of concepts that we deliver, and we complete a unit of, let's say, motion. So we talk about the concepts of distance, displacement, speed, velocity, and it seems like the learning happens to be linear. However, in the new curriculum, we may be jumping from motion to electricity, from electricity to quantum theory, maybe. So we are going to be able to make these connections in teaching. Concepts vary in their level of abstraction and universality. They can be organizing ideas that are applicable in many contexts and have relevance both within and across subject areas. So across subject areas. So when I'm a physics teacher, I teach physics, but I should be able to make that relevance with geography, with mathematics, with chemistry and biology at the same time. So therefore, it will provide a deep understanding of specific knowledge fields and help to organize knowledge further, as well as reveal connections between different areas of the subject. So let's look at the structure of the syllabus and conceptual understanding. In the new diploma program, no, this is not the poll I wanted now. Sorry about this. The poll has come after this one. Let me just finish this and then we will have another poll. The structure of this physics syllabus is intended to promote concept-based learning and teaching that can be connected through three concepts: energy, particles, and forces. So this is the physics part in which I feel very comfortable to talk about. Now the biology. The syllabus comprises 4 themes, each made up of 2 concepts, form and function. I put this in red on purpose. I'm going to ask you to see if you can notice why I put this in red later on when we discuss the concepts covered in the middle years program. So the biology teachers may be thinking about form and function. It may make relevance to them. It doesn't really resonates with me, to be honest. When I compare the concepts in physics and look at the biology concepts, it doesn't resonate, but we'll see how it goes. There are 2 organizing concepts in the chemistry roadmap: structure and reactivity. Each of these concepts is subdivided into topics and subtopics, which are all connected through the idea that structure determines reactivity, which in turn transforms structure. So there is kind of a cycle there. Structure determines reactivity, which in turn transforms structure. This is also making sense considering the chemistry concepts. But again, when I make a comparison, there is a shift in understanding of concepts from physics to biology and chemistry writing. So considering the concepts that we are focusing on in the new diploma program, what do you think the key concepts are in the MYP curriculum? And those 30% of the participants should be able to get the correct answer straight away. So can we have the poll, please, right now? So the question is, middle year sciences program focuses on 3 key concepts. Which of the following do you think would be the 3 key concepts in the MYP sciences?
It's quite competitive right now.
Half of the participants have answered that,
yeah.
so you can take your time. Try to see the commonalities between the options and the concepts that are introduced, that will be introduced in the new diploma program. So there are more participants than the one at the beginning of the session.
Currently, there are more attendees right now.
So everybody answered it, yes? And I have got, can we share the results? Can everyone see the results? So 44% says form, energy, and structure. Another 44% says particles, energy, and function. And I can understand why, I guess. So they have somehow common theme in physics, biology, and chemistry. So 11% says form, function, and change. Change is not one of these key concepts in the diploma program, and only 1% goes for form, function, and change. So interesting enough, no one has given the correct answer. And this is what happens in physics classes also. When I ask prior knowledge, students never give me the correct answer. And this is making the learning more interesting, I guess. So in our next slide, we will be looking at the map of concepts in the MYP program. And that will include the key concepts highlighted for sciences. Those are change, relationships, and systems. So this has been already in place for some time. So these are the key concepts, and in the MYP program, different subjects have different key concepts. Students focus only 3 key concepts in the sciences, that is change, relationships, and systems. And from now on, when they move on to DP, they will not see these key concepts, but they will be seeing some other concepts in physics, biology, and chemistry. They will have an idea of what a concept is, but it is not going to be repeated the same. So every unit in the middle years program starts with an inquiry statement. Ideally, this inquiry statement should be constructed with the student's input. But generally, speaking from my experiences also, it is written by teachers, and we have to include one key concept into that inquiry statement. And that is going to be our focus throughout the unit. And students should have the understanding of that concept. And they should be able to apply that concept or make connections to that concept in other subject groups. So for instance, when we have a communication link in our subject, students should have been exposed to that key concept in another subject, and therefore make a connection to communication between sciences and any other subject that they studied. In addition to key concepts, there are related concepts that every unit in the middle years program has to include 2 of the related concepts. And those related concepts in physics there are how many of them? There are 12 of them. So these are the concepts that we focus on in the physics curriculum. It does not include energy, forces, and particle. So now I am having question marks in my mind also. I don't know why there is no continuation. Oh, there is energy. Sorry, there is energy now. Is there forces? Oh, I noticed something new actually while I'm presenting. Energy is here. Particle and forces is not here, is it?
Yeah. There's
Right.
form and
So
function.
now there is one common, but the 2 other is not all in the physics related concepts. Function is going to be a concept that will be covered in biology, for instance, in the diploma program, once students complete the 5 years middle years program, and the diploma program is a 2 years program before the university. So let's look at this is related concepts in physics. There must have been biology and, okay, there will be biology and chemistry, but before that, let's look at an example. Consider the following sequence of 3 concepts. Now, I'm going to show you 3 concepts. Understanding of the concepts of ultrafiltration is part of understanding of excretion, which in turn helps to develop an understanding of form and function in biology. So this is an example of how we are going to map the concepts starting from a concept in biology, moving to a larger concept, that will include ultrafiltration, that is part of, for instance, excretion. And then we are going to make a link to either form and function. Another example in chemistry would be collision theory. Is a component in understanding chemical reactivity, for instance, which in turn helps to understand and helps to develop an understanding of change in chemistry. Again, change was one of the key concepts in the MYP program. So the sequence could be extended further to look at concepts such as particle, collision, reaction, all of which provide a basis for understanding of collision theory. Now, I'm going to pose a question for you to self-study. What if I give you thermal radiation? How would you come up with concepts that you would link to? Thermal radiation. Miss Emina, do I have access to chat? Yes, I have. So I think we can make this at this stage. I would like to make this a bit interactive. So I want you to consider thermal radiation right now. And what concepts do you think you can link thermal radiation into? So let me write this in here as well, thermal radiation.
Our attendees can also use Q&A.
And you can use the chat dialog box to put your ideas on what concepts that you have seen so far in the presentation that you'd like to connect to in your teaching. Any volunteer to put any answer in the chat?
I'm not sure about the chat, but they can still use Q&A and share those as a question, and we can read them here.
Open it. No open questions, it says.
No.
Yeah, Q&A. Okay. Is there any answer so far?
Let me activate the chat. So chat is now activated for our attendees too. Please feel free to write your answers to Mehmet's question.
So what concepts do you think can you link thermal radiation to? If you happen to teach thermal radiation, what are the concepts as a science teacher? Or even if you don't have a background in science, in teaching, what do you think thermal radiation is connected to? Shall we finalize it? We don't have any answers. Do we have any answers so far?
Not in the Q&A section, but so, maybe as we go, it comes to the
so
chat.
moving forward then.
Please.
Thermal radiation is a component in the understanding of energy, which in turn helps to develop an understanding of change in physics, for instance. But I'm sure you can come up with other connections and map thermal radiation to different concepts. We continue with the structure of the syllabus and conceptual understanding. In physics, we focus on 3 concepts: energy, particles, and forces. There are 5 organizing themes in the physics syllabus. So these are not necessarily topic or chapter, but themes. And each of these themes is subdivided into topics. Space, time, and motion includes the topic of kinematics and rigid body mechanics. Fields, for instance, includes the topic of gravitational fields and induction. Nuclear and quantum physics includes the topic of radioactive decay and fission. The study of sciences enables constructive engagement with topical scientific issues. So by contextualizing physical, chemical, and biological concepts, scientific knowledge claims can be evaluated more effectively, and informed choices on such issues as human health and the environment can be made. Teaching the content of the course in relation to specific contexts supports the pedagogical principle of teaching in local and global contexts. As part of the approaches to teaching framework and offers a number of advantages. First, it helps students relate their learning to genuine applications, highlighting the relevance to global issues. as well as the significance in students' own context. Second, it develops an appreciation for the interaction between scientific solutions and their implications, be it ethical, environmental, or economic. In the next video, in the next slide, we are going to watch a video in which we are going to contextualize learning. In a context of electric vehicles, we will be talking about global contexts, and the global context will be globalization and sustainability. We will be looking at applications of sciences in physics, chemistry, and biology, as well as interdisciplinary units in mathematics and geography also. We will discuss implications from ethical, environmental, and economic point of view. So right now, the page that I am sharing with you is a pre-release material for an interdisciplinary unit in the middle years program. Every year, students take an interdisciplinary exam, and this year it was science and math. And the global context is globalization and sustainability.
Battery technology is responsible for innovations in technology, such as smartphones, tablets, and laptops, and electric vehicles. Electric vehicles are the globally accepted transport of the future.
So now, imagine that we are constructing a unit around an electric vehicle, and we are expecting number of electric vehicles in the future to increase. And in this graph, for instance, we can teach students linear or proportional relationships. This is part of mathematics also. This is interdisciplinary. And in connection to the virtual reality lab, so we can take students in time and give them an experience of how would the roads look like with many electric vehicles in 50 years from now on, for instance.
But there is an environmental cost to this battery-powered innovation. The lithium-ion battery technology aspires to a fossil fuel-free society. However, lithium-ion batteries are made with metal components, such as cobalt, nickel, and manganese.
At this point, for instance, we can talk about atomic structure of different metals, different elements. We can study periodic table. What else we can do? We can go through the physics concepts of potential difference. So we are constructing a battery with different metals. Which combination of metals do they think would produce the biggest potential difference, for instance, would be an inquiry question that we can raise within a context rather than giving them an experiment to study which of the metals would produce the highest potential difference. So many schools, for instance, may be doing a lemon battery or a potato battery having zinc, aluminum, and copper. And combination of those two will give the highest potential difference. That experiment is very common, but it doesn't have a context. So having a context of a lithium-ion battery and having different metals will somehow encourage students to apply their knowledge in a real-life application.
However, lithium-ion batteries are made with metal components, such as cobalt, nickel, and manganese. Most cobalt is mined in the Congo. Human rights groups have exposed severe ethical and environmental issues in mining operations, such as child labor and pollution. Fatal accidents in informal mining practices and human exposure to cobalt dust makes the process of mining cobalt hazardous.
We can have connection to biology. The cobalt dust is hazardous to health. How? Again, with the use of virtual reality, lab and VR technology, we can take students to different parts of the world and have the experience to be in a mine, for instance.
Also, the extraction of cobalt requires a process called smelting, which emits sulfur oxide and other harmful air pollutants.
Sulfur oxide is something that we talk about many times in science classes. Now, we are using that in a context. This web page somehow gives an error, so I have to restart.
Lithium and other harmful air pollutants. Another important component of these batteries is lithium. More than half of the world's lithium supply comes from the arid salt flats of the Atacama Desert. The process to extract lithium uses significantly large amounts of groundwater, resulting in a decreased water supply and less accessible water for local agriculture. In the Atacama Desert, lithium mining companies have used 65% of the region's water supply.
We can link this to environmental sciences, earth sciences. We can link this to geography. We can take students to Atacama Desert with the VR technology. We can ask them to study rock formations in that desert. And we can also have connection to individuals and humanities lessons in which they study environmental impacts, social impacts of using electric vehicles. We talk about in the video, it talks about child labor, it talks about misuse of or violation of human rights, let's say. So it makes great connection between science and other implications of science that could be ethical, social, or environmental.
Lithium mines can also be found in Tibet. In 2016, there was a large chemical leak at a lithium mine in the Tibetan highlands. As a result, the river was severely polluted, and several fragile ecosystems on the Tibetan plateau were devastated.
So we also encourage our students to look at the environmental impacts of sciences. And this is another example of having electric vehicles.
Thousands of animals, including fish and local wildlife, which relied on the water from this river, were killed. Many of the components of an old lithium-ion battery in a smartphone or laptop cannot easily be recycled, and most end up in landfill. The components are highly flammable and are responsible for fires and contamination of local.
Again, the unit of combustion in chemistry can be studied in connection to recycling batteries. During the video, we have been talking about many parts of the world: Congo, Chile, we talk about Tibet in China. So that is part of globalization. So when we are driving an electric car, the parts may be coming from different parts of the world. It is not necessarily local anymore. So this is part of globalization, that we are having that context in our science classes.
Components are highly flammable and are responsible for fires and contamination of local environment at waste facilities. However, the news is not all bad. Old lithium-ion car batteries from electric vehicles have the potential to be repurposed. Research facilities are already working together to repurpose old lithium-ion car batteries in other applications. Car manufacturers are developing cost-effective technologies to recycle 100% of the components from lithium-ion car batteries. As demand for electric vehicles continues to increase, waste lithium-ion car batteries have the potential to become a serious environmental problem.
Again, in here, we can make a connection to mathematics and talk about scaling, for instance. With the use of VR technology, we can design labs to find ways to recycle the ion lithium batteries, for instance. So in this video, we have been talking about quite many different connections and areas, and that I have been talking about in the presentation. Going back to my presentation, I'm going to move on to another example of making connection with this unit, for instance. So we can provide these flyers to students, and when we look at the sustained solar car, for instance, on the left side, it has information about the average number of charges per miles. It has information about distance traveled, the number of charges, so on and so forth. So in this context, we can deliver the content of distance and displacement, for instance. On the right side, you are going to see oxygen and hydrogen at the center of the car. We can make a connection to the chemical structure, the atomic structure of these elements. We can make connection to reactivity of these elements or reactions that may take place. So before I move on to concept-based inquiry, I would like to look at a video in which the VRLab is in place. So I'm going to stop sharing right now, and we are going to go through a VRLab session. So this experiment is Young's double-slit experiment. In this experiment, we see waves' dual nature. It behaves like wave and a particle. And students are taking measurements in which they can make mistakes, they can make measurement, there are measurement uncertainties here. But this is an isolated experiment. So we have to somehow use this experiment in a purposeful manner. So this will be the next challenge for the teachers of DP to provide a context for this experiment. In this video, you are seeing that students are collecting data, and those are the skills that are expected for DP students or MYP students to have. Data collection, evaluating data, processing data. So after they collect data, they will be able to plot a graph and analyze the results. And this is also an experiment that is difficult to purchase or maybe difficult to obtain. With the help of VR, students are able to have access to data collection using advanced equipment. Now you are seeing a circular motion experiment. Again, most of the time, teachers, first of all, teach circular motion, all the theory, and apply that theory into a practice in an experimental setting, which I don't think that is an inquiry learning. In here, for instance, we can continue with our electric car example and consider a car is taking a turn in a circular motion. And in order to have a safe ride, students can analyze the effect of the mass of the car, the effect of the radius of the curvature, so on and so forth in an experiment. So this is also an experiment that can be contextualized, and in their tablet in here, for instance, they have access to the theoretical data. After they collect data, they will be able to evaluate their hypothesis, evaluate their results based on the scientific knowledge. The next one is Ohm's law experiment. Again, this is one of the favorite experiments for physics teachers. It is straightforward. You find the relationship between potential difference and current. But students need meaningful learning. So again, connecting this experiment to electric vehicles, for instance, students may try to determine the best wiring option in an electric vehicle. To be able to determine the best wiring option, students have to have an understanding of the concept of resistance. So students have to come up with their own inquiry questions and design an experiment and come to this lab and test their hypothesis, for instance. So this is a great opportunity for students to have a hands-on activity with resistors, connecting them to a circuit board, collecting data, plotting a graph, analyzing the results. They will eventually have access to the theoretical knowledge. And that is the non-linear learning that we will be talking about at the beginning of our presentation. The learning doesn't happen linearly. You don't start teaching one unit, motion, circular motion, I am done. It doesn't happen that way. So I'm going to start with motion, jump into circular motion, come back to the electrical circuits. So the learning will happen not linearly. It is non-linear. It is all over the place. And this is not easy. Thank you very much for this video, Ms. Gündoğan.
Of course.
So we can go back to the presentation. I have spent quite a lot of time by now. I planned this presentation for 15 minutes.
We
With the
have
new
it 10
adjustment,
more minutes.
now I was assuming to have half an hour. It has already been 50 minutes. I hope I did not bore you much, but I have got 2 more slides. Now it is time to combine conceptual learning and inquiry-based learning. So what is concept-based inquiry? So the new vision now in the DP program is not inquiry, but concept-based inquiry. In the inquiry-based learning, the focus was on the use of active questioning to derive learning. Now with the concept-based learning, we are going to focus on transferable understanding to organized learning. So we should be able to transfer the learning and understanding, and the combination of these two is going to make a concept-based inquiry. We talk about the challenges. There is a challenging work ahead of us in the coming years in the diploma program. And by applying concept-based inquiry with the virtual labs, I think the outcome in a table can be presented in this slide. I would like you to take a moment for you to read through. Again, I'm not expecting you to read them linearly. Just go from one box to another and see the outcomes of using the VR technology in applying concept-based inquiry, please.
This is quite inspiring.
This is the end of my presentation. Thank you very much for your time, for attending my presentation. I hope I was able to deliver the content in a clear manner. And by the end of this time, you have questions. If you have questions, I am more than happy to try to answer them or have a discussion maybe to find answers together.
Yes. Thank you, Mr. Gencer, for the presentation and sharing your personal experiences with us. I know that there are attendees teaching different curricula all around the world, so I believe this was quite interesting for all of us. Now I'd like to continue with the questions in the Q&A section. So please feel free to write to Q&A you can find in the bottom menu bar. And there I'll be directing them to Mr. Gencer. Okay, one question. Considering the hands-on nature of science education, how do you think virtual labs provide opportunity for collaborative learning and peer interaction in means of within the classroom and in remote learning? So this is one of the key points, of course, when it comes to the
yes, that's hands-on
virtual
nature.
labs.
Of course, we are. There's a shift towards hands-on learning. We are coming to the end of the year, and there are times somehow that I need to cover a class, or there are times that we give students free time, and they get together and in their devices, they connect in the same place in their devices. They're playing games, they're playing football maybe, which is quite a physical activity, but now in the same place next to one another, they are playing football using their devices. Similarly, in the classroom, we can get them together to conduct experiments in a multiplayer setting, let's say, in the VRLab, to conduct experiments. It's also possible, well, we are having World Cup tournaments in one country. It was in the Middle East last time, and many players came to Qatar to play football, right? Well, with the VR technology, it doesn't have to have people in the same place. I guess you can also design and conduct experiments, as we have talked about in our example. We can visit Atacama Desert, for instance, and the people in that country to somehow collect data from those rocks, and go to Tibet in China and see the environmental impacts of using chemicals, and bring them all in one lab to analyze the impact of different chemicals on water, for instance. So this is my answer. This is my question, answer to the question.
There's another question from Snow and it's that my question is similar to the first question. I believe concept-based teaching will be helpful to improve group for project work in IBDP. But what do you think about how we can use VR labs to create collaborative teamwork? I think you have answered some of it, but maybe you have some other.
Yeah, group 4 project is also a great way for students to show their interest to the global issues. In my previous school in China, for instance, there was a water fountain where the local people go and obtain their drinking water. And year on year, students work on that water spring to collect data, to guide the local people for responsible uses. One of the challenges students had in that project was to determine a way to measure the water quality, for instance. So with the VR technology, they cannot literally get that water tested in a VR lab. However, they can have access to the experiments that test the water quality. Because in the lab setting that we have had at the school, we didn't have the resources to be able to test the water quality. And that enables, so in that case, in this sense, students can somehow design experiments and apply that design using the VR labs. So we can have different examples depending on the context. It depends on the context, really. It's important to have a maybe combination of the real life experiences with the VR labs. So one of the things that I wanted to also talk about is the difference between simulation and VR labs. In a simulation, generally it is a lab in a setting, it's two-dimensional. We are taking that two-dimensional experience to the three-dimensional experience. VR also enables us to somehow create a space for an experiment. So if you are talking to the content creators, you can design a lab environment using VR. Even these days, my students show me a video which looks like a VR. They take their tablet up and down and it seems like three-dimensional. So the technology allows us to go in different directions.
Mhm. Thank you. One other question, just let me check. Okay, it's about the strategies. So what strategies can teachers or should they employ to effectively integrate virtual labs into their syllabus? Do you think this can be strategized?
Strategies.
Yeah.
Well, whether it is VR or any other lab work, I am a big favor of starting any unit, any lesson with an experiment. That to derive inquiry, to drive students to ask questions. And same with with traditional experiments. VR labs can be used straight away, at the beginning of a unit, and get the students to explore the materials, make them understand what the measuring tools are used for, how they can use it, and then let them design their experiments. Let them ask the questions that they have. They should come up with questions. This is what I used to do in the inquiry-based learning. Now, I have to somehow put that experiment into a context. I have to come up with new strategies actually myself as well. So before giving them that experiment, I think I have to provide them a context. And within that context, they should come up with questions. And with that question, to be able to answer that question, I should be able to guide them to an experiment in which they can either go to a VR technology or a traditional experiment. So this is, I'm not sure if I answered the question. If I keep talking, I guess I may have different answers to that question too. So this is just one strategy
That's such a
to my mind.
subjective topic, yeah. There's one other question, but maybe this is for me to answer. So the question is that, are there options to add more labs that match the concepts that we teach in VR Junior? The VRLab Junior is our middle school laboratory. So it includes experiments that are available for middle schools. And it says in your current offerings, there are many gaps in the content for my grade level. So this is actually something that you should be reaching us. So if you have that sort of a question, please reach us, because within one experiment, we actually allow students to conduct multiple experiments. So with one setup, they're able to conduct different topics that are that's possible to perform with that exact setup. So one experiment might be covering a couple months of experiments with only being one experiment. We share this in detail. If you send us your syllabus, we map our experiments according to that. So you would have a detailed information on what is the percentage we cover for the subjects you teach. There were two more questions, Mr. Gencer, then I will not hold our attendees more. As an educator who has embraced virtual labs in the IB programs, could you share a personal experience or success story that highlights the benefits or the impact of using virtual labs on student engagement or understanding of scientific concepts?
This is the question to me, right?
Yes, this is a question to you.
Well, to be honest, I have to be honest, my students did not experience VR labs. I don't have access to VR labs. So I don't have a personal experience, to be honest, teaching with VR labs. But I wish I can have access, and my students have access to VRLabs, but I did not have the opportunity to offer VRLabs to my students.
There was, yeah, there
Yeah,
was.
there was another question about the feedback. I was going to answer that
Yeah.
question. I on a daily on a day-to-day basis, of course, I use simulations and other online resources. And there are students who like those experiences. There are students who doesn't like those experiences, and this is where differentiation comes into place. I think there's no one size fits all. We should provide them as many opportunities as possible, and not at the same time maybe, but there will be time that the students will there will be students who will enjoy VR. There will be students who will enjoy hands-on. There are students who enjoy the mathematical aspects. So it is our, I guess, duty to offer them as many possibilities as possible, and expose them to the innovation that they may be using in their life in the future. So imagine, when I remember my student life, that was the time when we didn't have computers. Computers were introduced in my student life. Students liked it, some students didn't like it, but in the end, now everybody has to use it. Same with the VR. VR has a lot of applications in architecture, in fashion, in many different fields.
No.
So it is something that may be in their life, whether they like it or not.
So it's all about literacy. That's what I believe. So once they have that science literacy, technology literacy, and that adaptation, which everything requires that adaptation, whether it's technology or anything else. They are kind of luckier than the other generations, because they have some sort of default adaptation just by being in their age. So there's only to take this and take advantage of this and adapt students, because they are quite ready to be adapted. But maybe educators are the part that we should be considering on adapting more. That's my personal view, actually. So there is one more question, Mr. Gencer. So on, okay, it's about critical thinking and problem-solving skills. How do you think virtual labs foster those compared to the traditional lab experiences about critical thinking and problem-solving skills?
How does it promote critical thinking? So actually, in that question, there is an assumption. We assume that having experiments promotes critical thinking, which is not necessarily the case. So considering Ohm's law experiment, for instance, if you teach them what Ohm's law is and then give them the experiment to apply it, students will not take any advantage of it. I remember an interview from a very well-known CEO who didn't like science classes at all, because he thought that it was just a repetition of something that has been invented already ages ago, which they used to, they were trying to do it in a very primitive way in a science classroom. So that was the moment that I felt like, wow, such an insight, such a student who finds those experiments primitive. So we have to somehow, as we discussed in our presentation, integrate those experiments in a way that they are innovative and promotes critical thinking. And then if we can do that, no matter what you use, whether you use VR or traditional technology, that will promote critical thinking. So the question is, how do we do that? And I think I try to answer that question from my point of view. But in the learning journey of a teacher, I think students are the ones who are going to answer that question. you are going to get that feedback from the students. And by having that interaction, I think you will find your own way in the teaching. That's how I experienced.
I totally agree that. I think that's all the questions. Again, I'd like to thank all of the participants for joining us today. And I would like to also thank Mr. Gencer once again for taking the time and sharing his experiences. This was such a fulfilling webinar, and our webinars will continue on different topics. You can follow us on our social media accounts to know more about them. I wish everyone a great day and end of the week, and we see you in the next webinar.
Thank you. Bye-bye.